Hi everyone, welcome to my channel and welcome to this video. So in this video we are going to discuss about Linux procfiles, or rather the Linux procfs or procfile system. And we'll see what procfs is, what kind of files does the procfs hosts, why is it used for, and not only that, we'll try to create a procfile ourselves. Like we'll try to create an entry, we'll try to create a procfile in the procfile systems ourselves. So in my last video, as an example of a Linux kernel module, I built a Linux character device driver from scratch, right? Which would expose a file called counterdev. And whenever you would echo a number to that device file, it would add that number to an existing sum, right? It would maintain a running sum of whatever number you input to that file using echo. So we called it counterdev. So in this video, we'll be extending that kernel module. We'll be extending that character device driver, and we will make it expose a procfile in the procfile system, right? So what it would do is we would try to expose a metric, or rather a stat, in that procfile. Like whenever someone would cat that procfile, we will call it, let's say, counterdev stats. Whenever someone does a cat on that counterdev stats procfile, it would show some stats about our module. As of now, it will show only one stat, and that would be the count of numbers added so far, right? So let's say you do a echo 10 and then echo 20. So the device driver would sum them up, and it would store the number 30, which you can again see by doing a cat on the device file. But at the same time, the proc file would output the number 2, because we have inputted two files, or we have fed two files to the device file. So as and when you will feed more numbers into the device driver, the proc file would maintain a count of the numbers fed to the device driver so far, right? So whenever you do a cat /proc/counterdev stats, it would just output a number representing the count of the numbers you have added so far, right? So that's pretty much what our proc file would do. And in this process, we will see how we can make a kernel module expose a proc file in, or create an entry in the procfile system. So yeah, as always, without further delay, let's get started. Okay, so before adding further code to our device driver, our counterdev device driver, let's try to see what procfs is and what kind of files it exposes and things like that. So if I go into /proc in my present Linux machine, currently I am running as I've mentioned it a number of times in my previous videos, I'm running Ubuntu 20.04. I need to update it very soon, but yeah, I'll do it sometime. But yeah, currently I'm running Ubuntu 20.04 focal fossa, and my kernel version is, let's see, it's 5.15, right? Okay, so let's see what kind of files are present in the procfs. So you'll see that the procfs contains a lot of these numbers like this. Each of these number represent a folder, a directory, and interestingly, each and every number present here basically represents a live process in the system. And I did touch upon this in a bit of detail in one of my videos where I was building a container from scratch, where I was discussing about namespaces, namespace isolation, C group isolation, how to hide other processes when the process is running inside a container, how we could mount a new procfs when we are starting the container to hide the system processes or the host system processes. So there I touched upon this procfs a bit. So if I go into any such directory, what I'll find is a number of other files which will expose some information about the process this directory is representing. Some of the other files, some of the other popular files that's present in procfs is CPU info. It just gives you all details and information about your current processor, the number of cores it have, the features, the model name, all those kind of things you will get inside CPU info. If you want to know about the present memory, it's the memory stats, you can do meminfo. So it will give you a number of stats about your memory, and yeah, you can check this out, and these are pretty good for debugging and knowing the current stats about your present system. You have got something called disk stats as well, right? And these are pretty much in parsable formats, like something you can parse using a script or your program. So this gives you the various stats about every device, and you can read online about what each of these numbers mention. You will get things like free space occupied, number of inodes, and all those kind of things here. So let's see what load average has yeah, it has got the standard 1515 load average, and you can just play around with it and you will find a number of such stats or metrics that the kernel exposes for user consumption using this procfs or procfile system, right? So procfs is the short form for procfile system. Now let's you know what, let's go inside. Let me split my screen, and what I'll do is I'll write a very tiny python file. Let's go inside this folder, this directory itself, and what I'm going to do is I'm going to write a very tiny python program called p.py. What I'm going to do is I'm going to create a function called main. Let me import os. I'll get the PID of this process, and then what I'll do is I'll simply import time, and while true I'll simply, let me take c equal to 0. I'll simply print the counter, which is c, and then I'll do c plus equal to 1, and I'll sleep for something around 2 seconds, let's say, right? And that's pretty much it. I just want a long running process. I could have simply done sleep thousands or something. It's just that I wanted to see that the program is running fine, so I'm just printing out something. Okay, let's see if it runs. I believe it was get PID. Let's just quickly fix this. So let's see if it runs now, and it will keep on printing 0, 1, 2. One thing I forgot to do is I forgot to print the PID itself, which is the main thing that I need. So I'll simply write PID inside bracket, of course. Okay, so this is the PID that has been assigned to this process, this Python process, and this is 16719. And if I now do a ls, I should somewhere see this same process number and this PID, and here we go. We have 16719 in its procfs. So now if I go inside that 16719, I see a number of files and folders, right? So let's see what coms is. So com stands for command, the command I have used to execute the script or whatever executable or binary I'm running. So in this case, the command used was Python 3. Let's see what else I had given while running the code. So what I executed while running this script was Python 3 p.py, and there you have the entire command line. Right, so com stands for command, as I just mentioned, and that's why it has only got Python 3, but the entire command line was Python 3 p.py. You have got some other stuff as well over here. You can see what environment was passed to the program. So these all environment variables would be available to the running script. So you see, you get so many stats and so many information about a running process. You can check the process stats using cat stat, and this will give you various checks about the process that's running. And again, you can always use the procfs man page or Google to find out what these numbers mean. I do not remember at this point of time, but yeah, whenever I need something, I just Google and find out what a particular number gives, what a particular number means, and look at another thing, like it's nicely in a parsable format. All you need to do is read this file, get the data, and parse it so that you can know the value of a particular metric. It also shows you the namespaces. Let's go inside that. Let's do ls-l. It shows the various namespaces that this process is using. If you would see, these are all the these namespaces are the same as host's namespace. If you simply go into PID1, okay, if you go inside PID1 and you do ls-l ns, okay, so you will see that the IPC namespace being used is 1839. PID namespace being used is 1836. Of course, it has to be same. That's why it's able to see the other processes as well, 1836. So yeah, so you can get a quick look at the namespaces also your process is using. And so in case you have separated out the namespaces, from here you can find out which is the namespace that you created while launching the process. So that's the overall utility of procfs. It exposes a number of metrics, information, stats, or whatever you call about processes, the system, and anything and everything through these files. So the Linux exposes a number of metrics, information, details about processes and the system itself using procfs, right? So that's one of the main utilities of procfs. It can also allows you to configure kernel parameters using, like, you can write to procfs, and that can also allow you in certain cases configure kernel parameters, although it's no more the recommended way, because back when procfs was created, it was created in a kind of disorganized way that you can pretty much see while exploring procfs. So to standardize kernel parameter tuning or update, we have sysfs now, which I'll talk in a separate video, not in this one. So procfs, usually the kernel devs or the device driver devs try not to use procfs for tuning kernel parameters or device driver parameters. They usually try to use sysfs. So procfs till date is still used for viewing this important matrix, information about processes and system, right? One other important or interesting thing now about procfs is, if I just ls-l head-n20, if you see the size on disk of each and every file on each of these directory, or even if I cat CPU info, which I just did, cat CPU info, you will see that it's printing out data, right? It's printing out data, and you might think that since it's printing out data for you, the data might be stored in CPU info file, which means the file would have it would occupy some bytes or some space on disk, right? That's what we would usually think. But however, if I do a ls-l CPU info, you see that it occupies no space at all on disk, right? It says 0. But the question is, how is it possible? How can a file occupy 0 space or 0 bytes on disk, but yet it contains so much information, right? Where are these coming from? How does it print out so much data and yet occupy 0 space on the disk? The reason is, whatever data you are getting from a procfs file is not stored in that file, right? It's not stored on disk. The kernel is generating the data for you on the fly and spitting it out to whatever command you are asking, to whatever command you are using or utility you are using to read the file, right? So in this case, the moment cat tries to open this file and read something from the file CPU info, the kernel generates the entire data on the fly and it gives to cat, which then prints it on the terminal. That's why it occupies 0 bytes on disk. So analogically, it works very similar to how character device drivers works, in the sense that in case of procfs files as well, you need to define handlers. You need to define, if you have seen in my character device driver kernel module video, I said that for every operation that we want a device file to support, we need to define a corresponding handler. If we want processes to read from the character device file, then we need to implement our own read function, and which becomes the read handler, and then we need to put it inside the filed operations struct, right? So similarly, in this case, if we want a procfs file to support reading from that file, then we need to define a read handler for that procfs file, and we need to put it inside either the file operations struct or the procfs operations struct, depending on the version of the kernel. We need to use one of these structs, and we need to put the read handler in that particular struct. So whenever you are trying to read from the procfs file, the read handler gets called, and in that read handler, the kernel developer or the device driver developer would put in the code, would generate whatever data we need, and it would send it to user space so that the user space utility can show it on the terminal, right? So it's in this respect, in with respect to IO, it works pretty similar to how a character device driver works. So yeah, again, so that's what we also will be going to do. We'll be going to define these handlers which can generate the data, or if we want to allow processes to write something to the procfs file, we'll have to implement a write handler, which we won't be doing in this case because we won't be allowing processes to write anything. We would simply be, for this procfs file that we are going to create, it will only support reading and opening, right? That's it. So yeah, that's pretty much how the procfs, that's pretty much what the procfs offers us, and how at a overview level how a procfs file works, or how a kernel module can create a procfs file and expose stuff or allow processes to read from it. All right, so yep, let's now jump into code and see how we can create our handlers and actually create our procfs entry. Okay, so this is where we left last time. This is our basic counterdev device, which is able to calculate the sum of running numbers that's provided as input to the character device file. Basically, it helps us to count the sum of, or maintain the sum of, the numbers that we provide as input to the character device file, right? And hence the name counterdev. Let's quickly go over the code once, although you can always go back and watch my previous video that I created on this as well. It's pretty straightforward. I'm not going over the basics of character device driver development or kernel module development because I have already covered that in the other video. Yeah, here we have our counter dev init, which will be called while registering the module with our kernel. And here pretty much we create the device file, we register the file operations struct. The file operations struct pretty much contains references to all our handler functions. For read, we have defined device read. For write, we have got device write, device open, and similarly device release. We have a function to deregister our module as well when someone does a rm mod on the kernel module. So in that case, it simply destroys the driver, and it unregisters the driver, and it also removes the character device file, right? We have a function called device open, which makes sure that it's being opened in an exclusive way, that says that only one process at any given point of time is able to read from it. Not only one process, but even in the same process there can only be one instance of open call that can be called on the device file before making another open call. The previous instance of the open call, previous fd that's returned, that needs to be closed. Okay, we have device release, which just resets the cas counter or the cas variable. We have also a device release function, which is called upon closing the file, the device file, and which simply resets the cas variable. We have got device write, which when you are basically doing a echo some number to this device file, it takes it converts it into a integer, it adds it to the existing sum, which is this one, num counter. We have designed it in such a way that it can only count or maintain the sum up till 999, after which it simply rotates back and again starts from 0. We could have gone higher up, but I just decided to stick to 999 as the upper limit. Similarly, we have got device read. Device read simply gets the present sum, converts it into a string, and provides it to the user. And in both these cases, we are using copy from user to copy a piece of data from the user memory segment to the kernel memory segment. And while reading, we are just doing the opposite. We are copying the piece of data from kernel space to, or kernel memory segment to user memory segment, and hence we are using copy to user. We have it here, yeah, in the device read function. Finally, we registered our init and exit functions, and that's pretty much it. And if you're already excited to see this module in action, you can simply skip to the part where I'm running this module. I'll put the timestamp in the chart below in the description section of this video. And then once you have watched it, you can again come back here to continue following. Okay, so let's quickly implement our procfs part. So for that, we need to make one new import, actually include, and that is linux/proc_fs.h. So now we will do a if def thing, and I'll soon say why we are doing this. I mean, I'll explain in a moment why we are setting up this macro. Actually, it's very self-explanatory, but still. This is the name of our profile, and we will call it counter dev stats. So just like counter length, we need a length for like the number of length, which will signify the number of digits, since again what this procfs file would export or expose to the user space is nothing but the total number of numbers we have counted so far, like the count of the numbers we have counted so far or summed so far. And again, that number, when we'll send it to the user space or the user memory segment, it will be in form of a string, which means we need to have a length for the string, which is basically the number of bytes, where if I consider every byte as a digit, we need to have a total length for that string. And I'll call it counted length, and I'll go with 21. So basically 20 digits plus 1 byte for the null byte, that is \0. So this is the variable that stores the running sum. Similarly, we will have another variable that stores the count of the numbers counted so far. And finally, for the string representation, we would need a character array. We will call it counted str. Actually, my bad. The actual length of the string will be 21, and the total length with the null byte would be 22, which is counted length plus 1. And we need a variable which will store a reference to the procfs entry or the procfs file that will get created, which will be pretty much called struct proc dir entry stats proc file. Next, remember, we would have to define handler functions for the open call, close call, as well as read call, the handlers that will be used when the corresponding operations would be performed on the procfs file. So let's quickly define those. Here I'll just define the declarations, and soon I will define the definitions as well. The definitions are pretty similar to the usual character device handlers. As I mentioned, creating a procfs file is very similar to creating a character device file. This is profile read. I made some typo. Okay, so now what we are going to do is we are going to register this, or register these handler functions with the operations, the operation struct. And here comes the reason why I defined the macros. So if dev have proc ops is defined, what we'll do is, so just like file operations struct that we use for registering the handler functions for the character device file or the character device driver, for procfs we have its own type of file operation struct, and that's called procops, right? But this procops came into existence only after kernel version 5.6.0, right? Before that, it also used the usual file operation struct that's used for character device file, I mean normal device drivers. But post 5.6.0, or actually from 5.6.0, there was a, like, procfs got its own type of file operation struct, which is called procops. If it's running on a kernel version which is greater than equal to 5.6.0, then this macro will be set, and we will be using procops. And let's quickly assign the handlers. Otherwise, what do? We fall back to the usual file operations structure or struct. We can simply copy paste this and we do a endif. See how this is getting blurred out, as if like my kernel version is not 5 point greater than equal to 5.6.0, as I said, as I showed earlier using, actually let me just quickly show you my kernel version. My kernel version is 5.15.0, so it's definitely above 5.6.0, but for some reason the IDE is getting it all wrong for some reason, but that's fine, we can live with this. Our counterdef init function will have a added responsibility, that is creating the procfs entry or the procfs file. So stats proc file procfs underscore name 0644. So it will be created with the permissions 644, that is only root can only read or write to it, anyone else can only read from it, right? Proc file fops. So if it returned a valid pointer, actually if it did not return a valid pointer, if it returned a null pointer, what do? We simply alert error could not initialize, and the name of the procfs file. Let's set the user for this procfs file. And let's give a tiny info which says the proc file is created. And that's it, that's our init function modifications. Again, we need to do the same for the deregistration function or the exit function. So we will remove the proc file and we will log that as well as an info log. Yep, that's pretty much it. And now let's come to the read function, which will allow users to read from the proc file. So we will have a file pointer, the buffer, the size of the buffer, of course, and the offset. Because remember, it's v, since we are on the other side, that is we are now operating at the kernel side, it's we who need to manage the offset as well, right? Which otherwise gets managed for us by the kernel. It will be very simple to reading the sum that we did for the character device driver. I mean the actual character device driver. So we will memset counted str to totally null string filled with only null bytes. Then we will print the num counted value as a long actually in the counted str string variable. And this is simply I'm getting the size of the counted str, the string variable. Now if offset is greater than equal to len c, or we'll also try to copy this string to the user memory segment into the buffer that has been provided. How much do we want to copy? As much as the length of the string is, so that's len c. So if the offset value is greater than equal to len c, which is the length of the string, or copy to user failed, we simply say reading finished or copy to user failed. We'll keep it simple, just like before. And we set rate equal to 0. The moment you set rate equal to 0, rate is basically the variable we are using for the return value. The moment you return a 0 value from this function, the client-side utility will stop trying. That's how most of the client-side utilities are usually engineered or usually developed, right? So for example, cat. So as long as cat will get a non-zero value returned from this function, it will keep on reading from the procfs file, which means procfile read function will get called continuously unless it returns a 0, which means nothing more is to be read and it will stop, right? Cat will stop trying to read. Else what we do, we simply increment offset by len c. So this is a standard way of maintaining the offset, but in this case this entire thing will run only once because as you can see, we are writing the entire counted str string at once to the buffer, because counted str is a really tiny string, and the buffer provided by most of the user space utilities like cat and all, they are pretty large. Like I was reading somewhere on 64-bit systems, the default buffer used by cat is as big as 8 kilobytes, right? So yeah, that's definitely a lot for this 20 to 21 byte string. Next, the simple procfs open, and you will soon see that there is pretty much nothing in it. That's it. Now procfs close. I mean, we are not doing any customization here. We are just defining them for the sake of it. Just as an example. And that's it. That's an extension of our initial counterdiv character device driver with procfs support, right? Let's see if it compiles on our local machine. And looks like it did not. Procfs defined but not used. Why? I did use it. Didn't I? Yeah, I did. Oh, I see. What's the problem is I used the wrong return type while declaring. So it will be int, and this will also be int. Okay, what's the issue now? Okay, let's see. Oh, another typo. Should have been a pointer. Okay, that's another typo. It's on line 117. And I believe all good now. It compiled without any errors. So now what I'm going to do is, once again, I am going to transfer the source directory to my Raspberry Pi Zero, and we are going to test on that. So let's boot it up. Also see how we are not doing cas for this, because this is pretty simple, and we are only reading, we are not even writing. So yeah, it's fine, like it doesn't need cas. And we already explored the cas, the basically the atomic lock in the other video itself. So I guess we can let go of it in this video. So what I'll first do, I'll divide the terminal into two parts or two windows. Okay, so now what I'm going to do is, in the bottom one, I'm going to SSH into the Pi 0, and I'm going to create a new directory called counter dev proc, and now I'm going to transfer or SCP the entire source from here to this new directory counter dev underscore proc on the Raspberry Pi 0. So let's do that. Okay, so we have the entire source here now. Yes, we do have, and I'm going to zoom out a bit in this one, and at the same time I'm going to split it again vertically, so both the terminals or both the windows in the lower half of the terminal is inside Pi 0. Actually I have it not SSH yet here. I'll do as well in this one as well, the right one. Yep. So let's go into /proc. This, we don't have anything by counter, and now I will build it here. Okay, done. And now I'll do the usual ins mod counter dev.ko, and it got inserted. Let's once do our dmesg, and yep, the device driver registration initiated. The device driver has been assigned blah 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 236. Device created on /dev/counterdev, and /proc/counterdev stats has been created. Let's see if it has been actually created. Let's try to do actually let's do a hyphen, let's have an else. Yeah, it has been created with permission 644. That is, only the owner can read and write, and the owner in this case is root. For others in group, it is only read, right? So let's try to read something from here. What will happen? Cat 0. Of course, we haven't inputted or we haven't provided any number to the character device yet. So let's provide something. Let's say 120. Char 120 sudo t /dev/ okay, again let's do 40, sorry 40 140. Okay, 120 140, that should be 260. Let's do 200. Let's do 20. And now let's try to read from /dev/counterdev. It's 480, right? It's 480. Again, we didn't put a \n after this, so that's why it's coming in the same line. But yeah, it's 480, which makes sense. And how many numbers did we provide to the character device file? We provided 4. Basically, the sum of this 4 is 480. Let's see what our stats file or procfs file reads now. And it says 0. But why did it say 0? Of course, because we have missed one big thing. That is, perhaps we have missed the most important thing, which is really silly, but I did miss it. So remember, we never actually counted. We totally forgot to count. How could we? But at least we know that the procfs file is getting created, so we have achieved something. But no worries, we will have to go to the device write file. All we have to do here is, once we have successfully updated the sum, we simply do a counted plus equal to 1. That's it, right? That's it. This simple thing we had forgotten. Let me once just clear out everything. Let me do an rm mod. What happens if I do an rm mod? Oh, it needs a sudo, of course. And do we have this anymore? No, it's gone. And let's do a sudo dmesg. It says procfile close, device driver unregistered, and proc counter dev stats removed, which makes sense. So let's build it once again. And it failed. Why did it fail? Let's try to compile on our host system once. Okay, I'm not very sure why. Oh, I believe there happened a intermix of both the different files. I'll just clean up this real quick. Let's do ICP once again. Actually, you know what? I do not have to. I don't know why I did a full SCP. It's not required. A full SCP is not required. That's actually bad, doing a full SCP. All I need to SCP is counterdev.c and the make file. That's it. I don't need anything else to build this. Of course, that's all I always needed. And now let's do another sudo ins mod. Okay, before that, yeah, everything got generated. So sudo ins mod .ko. Let's do a dmessage again. Yep, it has been created. Let's do a cat. It's 0. And once again, let's input our numbers. 240. Let's do 20. And let's do something like 50. And now let's do a sudo cat. And it's 430. Okay. Let's see what's the output of counter dev stats now. 4. Perfect. That's the total number of elements or the total count of the numbers we supplied to counter dev, and that got exactly counted correctly and got returned to us by counter dev stats proc file, right? And just like any other proc file, I guess I just showed this. Its size is 0, but it's able to return us 4. If you add some more, let's say 100. So again, even if this thing rotates, the count will still keep increasing as and when we add more numbers. Okay, let's see what's the. It's 880. It hasn't rotated yet. Yep, and it's 8. Let's do 200. So 200 would mean 1080, which would get rotated to only 80. Okay, that would be a problem. Let's see what we have here. Okay, it's still 8 because, yeah, this is not a correct number. Okay, so what we wanted to do is 200. And let's do a cat. Yeah, it got wrapped to, or it got rotated to 80. And now if we do this, we'll get 9. If we do another, let's just try one more. It's 10. Yep, so that's our procfs file, which is working as expected. It's giving us some stats about our kernel module, which we exposed ourselves. Now we know how a procfs works, how we can use it to expose stats about our modules, our kernel modules, what procfs is used in real world, in real life, the amount of the vast amount of highly important information that's exposed by procfs about the kernel, about processes and everything. And we also saw a very cool thing about procfs is that it provides you with so much information, but it does not take any space on disk because all the information are generated on the fly by the kernel or by the process, yeah, however you say it. So yeah, that's pretty much it for this video. And let me know in the comment section below how you use procfs in your day-to-day life. What sort of information you use procfs for? How do you rely? To what extent do you rely on procfs while you are debugging stuff? So let me know these things in the comment section. And yep, that's it for this video. I hope you all enjoyed it and see you all next time.